Hi folks, and welcome back to Physics with Captain Rod, making this video here to help you out with number 5 on the Unit 1 practice test. So in this problem we've got young Timmy here who's in a balloon. The balloon is 50 meters high and moving upward at 5 meters per second. Pretty fast balloon, but that's alright. Timmy drops his watch, and let's see, it says to draw a velocity graph to describe the motion of the watch assuming air drag is negligible. So what you have to realize is the problem really doesn't have anything to do with the balloon, it's about that watch. So I'm going to just use this dot for the watch. At the instant shown though, before Timmy drops the watch, it's all part of the system here. The balloon, the ropes, Timmy, and his watch are all moving up at 5 meters per second. So that watch is starting with the same velocity in this problem. So if we draw a velocity graph now for this watch, at t equals 0, that watch is moving at about 5 meters per second, according to the initial conditions of the problem. Now the watch's motion, it's going to go up slightly, but then ultimately come back down due to gravitational acceleration. In fact, after a second goes by, that watch is going to drop in velocity by 9.8 meters per second, and then another 9.8 meters per second, and then another 9.8 meters per second. That's because gravitational acceleration is down at 9.8 meters per second squared. That means this graph is going to look something like this. Now, this line has an equation that can be described like this: v equals a slope times t plus the intercept. All linear functions have this form. Remember in algebra class, y equals mx plus b. The slope is the acceleration. And the intercept you can read right off the graph. It's 5. So here's our function here that would tell us the velocity of the watch for any given time. Now what we're going to do is we're going to try to use this to write an equation for the position of the watch, like the height. And we can put a 0 anywhere we want. I usually start, put like zeros wherever your coordinate system launches from. So we would say that at t equals 0, the watch is at y equals 0. And what we're going to do is we're going to use this area here to calculate a delta y, a change in position. Now the reason for starting here and not here, this is a very specific point on the graph. That's the point where the watch has hit its highest point and then it's starting to come back down. If you use this point to write your equations are only good when that watch is here at the highest point in its loop. It's good no other time. So we're going to just pick like a generic time here to write our equations. So this is some time t. And then this vertical distance here is described by this function. So when we find our area, our change in x, it's going to be 1/2. The left-hand side of the trapezoid is 5. I'm going to leave the units out. The right-hand side is described by this function, negative 9.8t plus 5. And then times t. Now this is actually giving us our change in y, but if we measure y from where this thing starts, y initial is 0, this would equal y minus 0. I'm just going to put y. Clean this up a little bit, you're going to get y equals, what is it? It should come out to be 5t minus 4.9t squared. Now to figure out the time when it hits the ground, this was 50 meters, so the y-coordinate here would be minus 50 meters. And you'll be able to solve that for time. It's going to be quadratic. You'll end up having to use the quadratic formula. Equations in physics rarely factor. If you needed the speed, I don't know if the problem said that or not. No, it just says how long, that's the time, so you'd be done. But if you needed the speed, you could take that time, put it here to calculate a velocity. Hope that this video helps get you through that problem. Have a great day.